So this is the last section on stoichiometry, and you'll notice that both sequential and the solution stoichiometry aren't in your book, and this is where this is the more challenging course, and that's why we're doing some of the stuff that you wouldn't necessarily see in other courses. So what we're looking at here is solution stoichiometry, and what we're talking about is a lot of times when you're dealing with chemicals, they're not solids or gases, or even a liquid. A lot of times they're actually in an aqueous solution. So how do we deal with when they're in an aqueous solution? And some of the labs we've done, like some of the ones mentioned here, we've done them with aqueous solutions. Even like when we do the copper lab, we make our copper sulfate into a solution beforehand. So we're making solutions and using solutions all the time. An important thing to remember about solutions is that when we do solution concentration, we typically do molarity. And you want to remember molarity is your moles divided by your liters. So really, solution stoichiometry isn't really that different. All it is that you have to deal with molarity as a conversion factor. So it's kind of like a molar mass or anything in that regards that we've been doing before, a density, that kind of thing. So we're going to do two examples where you're using a molarity in a stoich problem, and hopefully that'll help. And then you can always do the practice problems that we give you as well. Okay, so the first thing here is we have excess lead-2 carbonate, and remember that just means we have lots of lead-2 carbonate. It reacts with a very certain amount of 3 molar nitric acid, and we want to calculate the mass of the lead-2 nitrate that's formed. So the first step, obviously, is to write a balanced equation. So we have the lead-2 carbonate added to nitric acid, we're making lead nitrate, and we're also making carbonic acid. All my charges are balanced here. I went back and balanced the whole equation, so I needed 2 in front of my nitric acid because of the H2 over here and the 2 nitrates right here. And then what we're doing here is I've been given a molarity of nitric acid, and I want to go to grams of lead nitrate. So you know that this is a molarity problem and has solution in it. You know you have to do this a special way. So what we do first, before we do stoichiometry, is we actually do a little molarity problem. So they gave us our molarity, and our molarity is 3 molar. And they told us it was 27.5 mils, which if we divide by 1,000, that gets us to liters, and it's 0.0275 liters, which I plugged right in here. So I'm just doing a little molarity problem first, solving for my x, which is my moles, and now I have my moles of nitric acid. Once I have my moles of nitric acid, now it's a normal mole problem. So we have moles of nitric acid, we can do our mole ratio right away, and again we're going from nitric acid to that lead nitrate, that one product we're making. So you can see it's a 1 mole to a 2 mole ratio from our reaction. And then the last thing I do is I want grams, so I look at my molar mass of lead nitrate, which is very heavy, and it's 331.2 grams per mole. And we would get that we would form 13.7 grams of this lead nitrate. So it's really just stoich, and then what we have is we have a little extra bit here because we have a molarity section to it. So you just have to kind of watch that when you're doing them. And one thing you want to be aware of, when we're talking about 27.5 milliliters of this, when we're talking about liters, we're talking of solution, like an aqueous solution. That's not the same thing as the gas ones with the 22.4 liters at STP. So you have to make sure, are you talking about a solution or are you talking about a gas for these problems? And last one we're going to do here, we want to know, we want to calculate the volume in milliliters of a 0.324 molar solution, and that just means molarity of sulfuric acid, and we let it completely react with 2.792 grams of the sodium carbonate. So here's the solution right here that we have. We know how many grams of sodium carbonate we're starting with, and we want to know how much of the sulfuric acid thing that we need. Sulfuric acid is not a gas, so that means it's definitely going to be a solution problem. So since we are given grams, it's going to start with normal stoichiometry. And if you look down here, I have my 2.792 grams of sodium carbonate. I divide by my molar mass, and then what I did is I did my mole ratio here. So I have 1 mole of the sodium carbonate, and I have 1 mole of the sulfuric acid. And then you have a choice. You can either stop here and get your moles and then do a little molarity problem, which is perfectly fine, or you can use this right here. We know that it's 0.324 molarity, or 0.324 moles per liter. So we can use this as a conversion factor, and what we can do here is we're in moles of sulfuric acid. So if we invert this or flip it upside down, the moles of the sulfuric acid goes on the bottom, so that would cancel, and we would be left with liters, which is what we want. We want the volume. So we can do this. If you do it the other way, you'll get the same answer. But we do this math, and we get 0.08130 liters. They want our answer in milliliters. So we just multiply by 1,000, and we get 81.3 milliliters for this guy. Hopefully you enjoy a little turkey over here. So you really just have to be sure, you have to have a plan for any type of stoic problem, and you have to really be aware of what type you're doing, because obviously molarity is different than a gas, is different than a limiting reactant. So just kind of keep that in mind while you're doing it, and hopefully this video helped.